Hello, everyone. Thank you for attending my talk on the reconfigurable, non-volatile, high-performance Metalens. In this talk, you will hear the three topics. The first one is related to the material platforms, which we leverage for constructing this tunable metasurface. The second one is about the design of the reconfigurable Metalens. And the third one is its implementation and characterization. So first, I would like to go through the advantages of the metasurfaces and the comparison to the traditional optical elements. So here you can see the lens, which sculpts the incident beam. This is the planar wave, and then after that, when it propagates through this curved piece of glass, it transforms into the spherical wave and goes to the focal spot. So you can look at this element as it creates a certain phase delay profile. Similar phase profile can be recreated with an array of sub-wavelength elements, and this kind of device is known as the metasurface. And the main advantages of the metasurfaces is much better swap characteristics, which stands for the size, weight, and power, and it also unveils the new way to new functionalities of these optical devices due to this sub-wavelength element control. And tunable, reconfigurable optical elements has always been the holy grail for the optical engineers, and the same is in the field of the dynamic metasurfaces. Here I would like to highlight several methods how the metasurface can become reconfigurable and tunable. And this ranges from mechanical actuation to orientation of the liquid crystal environment in which the metasurface is immersed. There is still a remaining challenge. So there is this need for creating a metasurface which has a wide tuning range, or ideally it would be nice to have if we can switch between the arbitrary phase profiles. There is a need for higher optical qualities and increased efficiency. And as a first step regarding our research, I would like to mention about the materials. So we used the germanium, antimonide, selenium telluride. This is a chalcogenide alloy. And as you can see, it has a pretty high refractive index of around 5 in its crystalline state, which is very attractive for all dielectric nanophotonics, where we would like to confine the field inside the dielectric with the high refractive index. And in addition to that, this material can be switched between the two crystalline states, and which results in the refractive index change of about 1.5. I would like to point out to the unique feature of this material that it has really low losses, particularly in the mid-infrared range. So the K here goes down to 0.5. And if we calculate the figure of merit, which is the ratio of delta N to the K in the lossy state, such as crystalline typically, it would be 100 times higher than the typically used GSST 225. And then we leverage this material platform for demonstrating a metasurface. In this example, this is a varifocal Metalens. So we have two states when the metaatoms are in the low refractive index dielectric state, amorphous GSST, and then we go to the crystalline state. And as you can see, by switching the refractive index, we can manipulate the focal spot position. So in amorphous state, the main focus is f1 at the distance 1.5 millimeter, and then it goes to 2 millimeters, and we call it f2. So from the perspective of the metasurface, or like the phase delay, what we're doing, we're basically shifting between the two phase profiles, which are represented here by the hyperbolas. And let me go a little bit deeper into our design principle. And I would like first to give you a simple example where we have two states, with the focal spot at f1 distance and the focal spot at f2. And here are the 2D phase maps. Previously, I showed you the 1D distribution. Now it's a 2D. And there are only two colors, black and white. And ideally, what we would like to do, we would like to find the design so we can switch between the two arbitrary phase maps. So in this example, how it can be done, we can just go pixel by pixel phase switching. And since we have only two colors, we need 4 transitions. In this example, can be accomplished by this 4 meta. So each of them serves as a phase delay switch. So depending on the state of the dielectric material, whether it's a low index or high index, this non-antenna can either change its phase response, like not change in this case, or drastically change it by switching from 0 to 180 degrees. So we need to find the geometries which would be either sensitive or not really sensitive to the change in the refractive index. And this principle can be further generalized for multiple optical states. So here's only 2. You can extend it to more than 2, and also a higher number of phase levels. So regarding phase levels, if we look at the optical efficiency, so if we have only 0 and 180, 2 phase levels, if we look at the optical efficiency of our Metalens, the highest we can get in the best case of like ideal meta atoms, we can get like around 40%. But you can see that this efficiency can be put even higher by introducing, by increasing the phase numbers by 2, factor of 2. So if we have, for example, 4 colors, 4 phase colors, then we can go like above 80%. Although we can go even higher, but there is a trade-off. Basically, the higher phase levels you have, then the more meta atoms you need to find, and there is also increased probability for having higher phase errors. So, which also in another way, it kind of reduces the fabrication tolerance. So we stopped on the midway for the 4 phase levels, or if you wish, like a 2-bit design. And I would like to walk you through the steps of our design process. So we started from the 2 phase maps corresponding to the 2 focal spots, F2 and F1. And after that, we did the discretization. So this is our 4 levels, which correspond to 0, pi over 2, pi, 3 over 2. They are indicated with 4 different colors. And at the end, we have searched for the meta atoms. And then when we substituted these meta atoms in a certain position, this is the phase maps which were finally achieved and were used for implementation of this meta surface. I would like to show you quickly the library of the generated meta atoms. So you can see there are 16. Why there are 16? Well, the explanation is that since we have only 2 states, amorphous and crystalline, or F1 and F2, and we have 4 phase levels, we need 4 to the power of 2 meta atoms, which is 16. So you can calculate further if you, for other levels, phase levels or multiple states. And I would like to direct you to the talk, which will be given by my colleague, Sensong Ang, on Wednesday. He will talk about how to find this meta-atom geometry or generate them on demand by using neural networks. It's indeed it's a big challenge, particularly in the case when we go into multi-state, multi-level meta surfaces, and here is a big deal of how to find that geometries on demand. And the last thing I would like to mention here is the characterization of the meta surface. Here are the 3 parts: focusing efficiency. Then we studied the point spread function, basically the Strel ratio, to confirm that our focusing is diffraction limited. And in addition to that, we also studied what is the contrast ratio between the 2 states of the Metalens. Here is the SEM of the fabricated structure. It was done by conventional clean room facilities, electron beam lithography combined with reactive ion etching of the GSST material. And this is our optical characterization. So here you can see in parallel the lens performance in the two states, in the amorphous one and when it's in crystalline state. You can see that both of the primary focal spots diffraction limited with the Straight ratio exceeding 0.9. We can look at the secondary focal spots, which are indicated here with the dashed line, and you can see that the contrast ratio is pretty high if we talk about like the power contrast ratio. So in amorphous state, it's 10:1, and for crystalline state, it's even better. It's 90:1. And in addition to that, we also achieved quite decent efficiency, slightly exceeding 20%. On top of that, we have also demonstrated the imaging functionality. In this case, we produce the images of the USAF chart patterns, which is basically the stripes. I think in this case, it's about like for one of the states, the resolution is around 7 micron, and for the other one is about 9 micron. So here you can see that we can produce the images with these metalenses. So in amorphous state, we clearly see the image of these USAF chatters in the focal plane f1 and almost nothing in the focal plane f2. And the similar thing when we do for the crystalline state. So it's clearly, it confirms that most of the functionality is as expected. And here is one more test where we have overlapped the two targets at the 45 degrees. So the distance between the two targets is exactly equal to the difference between the two focal spots. And as a result, you can see that with this metal lens, without actually any mechanical movement, we can first image the targets on one side of the focal plane f1, and then by changing the refractive index of the material, we can switch it to the focal point of 2. So as a result, we can demonstrate the diffraction-limited cross-free reconfigurable imaging. On that, I would like to finish my talk. Here you can see the summary of the 3 points which I was going to discuss today. And on that, I would like to leave that summary slide. And thank you for your attention, and I will be glad to answer your questions.